Hello, this lecture is about tributary areas and influence areas, two concepts that are commonly used to transform uniformly distributed loads on a slab, floor, wall, or roof into uniformly distributed loads or point loads that are acting on the structure. Let's get started. There are basically three types of loadings that we deal with when it comes to the analysis and design of structures. The first is a pressure loading. That is usually denoted with a lowercase q and is often in terms of pounds per square foot in the imperial unit of measure. The second is a line loading, where we denote that with a lowercase w, and that's often in the units of pounds per linear foot or kips per linear foot. And then lastly is the idea of a point load, usually denoted with a capital P, sometimes in units of pounds, but more often in units of kips. Now, when it comes to looking at civil and architectural engineering structures, the loads that we model, like dead load, live load, snow, rain, etc., are most often manifested in the case of a pressure loading. So the tributary area is a basic concept used in structural design to calculate loads for members. The tributary area is the hypothetically loaded area of a structure that directly contributes to the load applied to the member under consideration. It's basically the portion of the surface area, a roof, a floor, or a wall, receiving loads that may be assumed to be supported by the member under consideration. Based on the assumption that beams, girders, and columns are simply supported, the tributary area is usually defined as the area bounded by lines halfway to the next beam, girder, or column. Okay, consider this building. It's rather rudimentary, very simple. It's only 2 stories high, and we're showing the roof slab on top and then the floor slab below that. And what I'm going to do for sake of discussion is I'm going to make the floor and the roof transparent so we can see the beams and the girders below it. So I've added some transparency to the roof slab and the floor slab so we can see the supporting beams and girders within the structure, as well as some more of the columns. So let's go ahead and suppose that for this structure here, just for sake of discussion, let's suppose that we have a load of Q is equal to 100 pounds per square foot. Okay, and what we need to do is figure out how much load do we design each of the beams and the girders for. Okay, this is the framing plan for the roof of the building. Let's suppose that we wanted to do an analysis of the filler beams in this roof. Suppose we wanted to do an analysis of this filler beam right here. What we would do is we would go halfway to the next filler beam in each direction, so between those two and halfway between those two. And we would use those boundaries to define the tributary area for that filler beam. Then we would go a step further and we could define a new term that is referred to as the tributary width. And I'll call it T sub W. Sometimes you see it called TW instead of T sub W, whatever. It's the width that's tributary to that beam. We could do the same thing if we were interested in the spandrel beam out here like that. We could define that area there as the tributary area for the spandrel beam. And in that case, we go halfway to the next beam on the interior side, and we go all the way to the edge of the slab on the exterior side. So based on that, what we would do is come up with a line loading based on the uniformly distributed pressure loading that the floor is subjected to for the analysis of the beams. So back to our three-dimensional view, suppose that we know that Q is equal to 100 pounds per square foot, then knowing that these beams are each spaced 6 feet apart, we could say that the tributary width is equal to 6 feet. So therefore, our uniformly distributed load W is equal to 6 feet into 100 pounds per square foot, or we would have to design these for a load of 600 pounds per linear foot. That would be for the interior beam. On the exterior beam, it would be something smaller. Maybe we would have 3 feet on the inside and 1 foot on the outside. So we could say that W for the outside would be, say, 4 feet times 100 pounds per square foot. That would be equal possibly to 400 pounds per linear foot. And then we would do our analysis of those filler beams due to a line load like this, where W is equal to 600 pounds per linear foot there, and W is equal to, I'm running out of space, that wasn't very smart. W is equal to 400 pounds per linear foot there. So back to our framing plan for the roof, the same concept holds true for the girders. So let's suppose that now we want to look at this girder here, an interior girder. Then what we can do is go halfway to the girder to the left of that, describe one line, go halfway to the girder to the right, and then that would define the tributary area for that girder. And then similarly, we could say that this width here then is the tributary width for that girder. Okay, that works for an interior girder. We could also do the same thing for an exterior girder. So this would be the tributary width for that exterior girder there. Okay, back into our three-dimensional view. Then that tributary area would be translated into a uniformly distributed load in terms of pounds per linear foot or in terms of kips per linear foot. And we would do our analysis of that girder using the uniformly distributed load. Okay, one final idea is that back in our framing plan, what would we do about the columns? Well, when we look at a column, let's suppose we wanted to look at an interior column, that column there, for instance, then what we would do is go halfway between columns left and right, halfway between columns this way, halfway here, and we would scribe in our tributary area for an interior column like that. Okay, we could do the same thing for an edge column like this. We would go halfway left and right there, halfway left and right there. In this case, we would go with the inside like that, and we would end up with a tributary area for the edge column that looks like that. And then finally, if we were interested in the corner column, like this one, for example, we would go halfway to the next column in one direction, halfway to the next column in the other direction, and then that would define our tributary area for the corner column. So looking at the building again in 3 dimensions, that's what those 3 tributary areas would look like for the roof slab. So we would take these tributary areas, would be in probably units of square feet, multiplied by our distributed load of Q, and get point loads that would act on those columns. And one thing that's important to bear in mind, particularly with respect to columns, is that the tributary areas accumulate vertically as well. So there's also a tributary area for each of these columns associated with the first floor, not just the roof. And what we have to be cognizant of is that if we're looking at the loads that are acting in these columns, let's suppose that we're dealing with this one here, call this P sub R for P, the load that's in the roof, call this P sub F that's in the floor, then we could figure out the axial force that's in this column here is going to be P is equal to P roof. But then when we get to this, then P is equal to the load on the roof plus the load that's on the first floor slab. And in fact, the tributary area in this column is going to be equal to twice of the length times the width. So we have to be cognizant of the fact that tributary areas accumulate vertically when we look at columns. Okay, one tacit assumption that we made in defining these tributary areas is that we're ignoring the effects of continuity, and we're ignoring the idea that the slab is continuous, and we're assuming that it's simply supported over all of the supporting members. Now, how big of a deal is that? To look at some of the implications of that, let's go ahead and look back at the framing plan for the roof. And what I'm going to do is cut a section through the building like this and look at that cross section. So this is a cross section of the building. I've worked with Revit to make this so you can kind of see the concrete is represented there, and you can see each of the floor beam members cut in section. And when we cast the concrete is usually cast in one continuous pour, plus there's a metal deck in place often. If it's a reinforced concrete building, then the deck would be probably formed up with plywood or something like that. But in any case, the concrete deck is going to be continuous across the members. So a proper analytical model would be one that looks like this. So you have a continuous member that's supported at many locations along its length, in this case supported by the floor joists. Now, when we look at the tributary area or the tributary width for a beam, in this case, that tributary width is only going from halfway to the adjacent members. So this would be the tributary width. And the tacit assumption that we make in that is that there is a pin in this slab or simple support in this slab at every location over an interior support. So we ignore the effects of continuity entirely. Now, how important is this? How important is the continuity when we consider the analysis of a beam or a slab? Well, this is a model of a beam that's two spans with continuity over the center support. And if we look at the reactions for that system, we can see that the reaction at the center is 5/4 W times L, and at the reactions at the end are 3/8 W times L. However, if we look at the same system modeled assuming that it's simply supported over the interior support, assuming there's no continuity there, then the reaction forces are different. So we end up with a reaction that's a little bit lower over the interior support and a little bit higher over the exterior supports. So there is a difference in the reaction forces based on the fact that we're ignoring continuity, but it's generally accepted that the simplicity that's associated with ignoring continuity is more important than the minor differences that you would see in the reactions or in the distributions of load. Consider the floor framing system that's shown here, where we have wood planking supported by floor joists that are in turn supported by girders that are then supported by columns. Note that the planking or flooring in this case is structurally continuous over joist B. Suppose that we have a gravity load of 100 pounds per square foot, to keep it simple, and let's suppose that the floor joists are spaced at 24 inches so that the planking has a span length of 24 inches or 2 feet. If we ignore continuity and use a tributary width approach to determine how much load joist B has to carry, we can determine the tributary width by going halfway towards joist A and halfway towards joist C and determining that the tributary width is 24 inches. Then we can determine that floor joist B has to carry 200 pounds per linear foot of loading. If we look at joists A and C, and if we ignore the little overhangs on the outside of the girders here and here, then we can determine that each of these joists has a tributary width of about 12 inches and each joist carries about 100 pounds per linear foot of load. If we go back now and recalculate the load that the floor joists have to carry, but this time include the effects of continuity for the planking, what we would do is use the reactions that we calculated for the continuous beam a couple of slides ago instead of using the tributary width approach. For joist B, we would calculate that it carries 5/4 times the load of 100 pounds per square foot times a span length of 24 inches to determine that joist B carries 250 pounds per linear foot of loading. Considering joists A and C, we see that each would carry 3/8 times the floor loading of 100 pounds per square foot times a span length of 24 inches or 75 pounds per linear foot. The net result is that when we ignored continuity, we underestimated the load that the interior floor joist carried by about 25%, and we overestimated the load that the exterior floor joist carried also by about 25%. Still, even when the decking is actually continuous, the simplicity of using a tributary width approach often wins the day, and many engineers will simply ignore the effects of continuity in their calculations. While this is generally accepted when it comes to determining how much floor loading each of the supporting joists carries, continuity can be important in some cases when continuing the actual strength of the flooring. And continuity is definitely important when it comes to the analysis of beams and girders, but this is a topic for a different lecture. The next topic that we'll consider is the idea of influence area. The influence area is the actual area over which any applied load would have its effect felt by the member under consideration. So a member is assumed to carry no load outside of its influence area. So let's go to a diagram to illustrate that a little bit. Consider the figure on the left here, which is an interior beam. And if we caused a displacement in that beam, if we moved it upwards uniformly by 1 inch, you can see the displacement in the slab which and any part of that slab that is displaced would be part of the influence area for that beam. We could do the same thing with a column, as is shown on the right. If we take an edge column, for example, move that column vertically by 1 inch, and any part of the slab that is displaced would be part of the influence area of that slab. So that means that if we put a load anywhere on the influence area, then the beam is going to feel it. It's different than the tributary area. We could put a load on the influence area that isn't part of the tributary if we remember. Let me go to the next slide to try and illustrate a little bit better. This slide shows a roof framing plan again, showing the tributary areas for an interior filler beam and a spandrel filler beam. The influence area is the area that stretches all the way to the adjacent element. So in the case of the interior filler beam, it stretches upwards towards the next filler beam and downwards to the next filler beam. And that influence area would look like this. In the case of the spandrel beam, on the interior side, it stretches to the next filler beam, and on the exterior side, it can't go any further than the edge of the slab. So the influence area for the external filler beam would look like that. With respect to the girders, it goes to the adjacent girder. So in the case of the interior girder, it's going to go to the left to the girder along girder line A, and on the right edge, it's going to go to the right until we get to framing line C. So that is going to be the influence area for that interior girder. So any load acting in that hatched region is going to be felt by the girder. Same thing for the, similar concept for the exterior girder. It's going to stretch all the way from girder line A to B, and that's going to be the influence area for the exterior girder. With respect to the columns, we have a similar concept. So here's an interior column, column B2, and it's going to stretch to the framing lines of the adjacent columns. So all 4 bays are going to be included with that influence area for column B2. With respect to the edge column, C1, then we're going to include the adjacent bays for that column as well. So that's going to be the influence area for that edge column. And then finally, for the corner column D3, that's going to include all of that bay CD23. That is going to be the influence areas. So for an interior column, the influence area is the total area of the 4 bays that surround the column. For an edge column, it's the total area of the 2 bays adjacent to that column. And for a corner column, it's the total area of the bay adjacent to that corner. With respect to girders, the influence area of an interior girder is equal to the total area of the bays on either side of the girder, and for an edge girder, it's equal to the area of the bay adjacent to the girder. We can say in general that columns have an influence area that is 4 times the tributary area, and for beams and girders, the influence area is 2 times the tributary area. So this is a framing plan for the roof again, and we're going to consider the girder along framing line B2, B3, and we're going to consider the filler beams that frame into it. Here's one of them that runs from framing line A to framing line B. So the first thing I'm going to do is consider the loading on that filler beam. So let's take Q equal to 100 pounds per square foot again. And we're going to recognize that the girders are spaced at 6 feet intervals, so we take the tributary width as equal to 6 feet. So we can calculate the uniformly distributed load W is equal to 6 feet times the pressure loading of 100 pounds per square foot, or that's equal to 600 pounds per linear foot. So this load up here is W is equal to 600 pounds per linear foot. So if we figure out what the reactions are, we could say that the reactions for our beam are going to be equal to 1/2 of the total loading. So it's going to be 1/2 of 600 pounds per linear foot multiplied by the length of the floor beam is 30 feet. So that is going to be a total reaction of, 30 times 600 divided by 2 gives me 9 kips. Okay, now let's look at how the filler beams frame into the girder. So we have a filler beam here, floor beam, filler beam here as well. This is the girder. So the filler beams frame in with these joints on the with web connections. So we're going to have a reaction at the end of the filler beam acting upwards on the filler beam, and it's going to act downwards with 9 kips on the girder. So we're going to have end reactions for that filler beam of 9 kips. So what that means is at every girder location, we're going to see a net of 18 kips of force. All right, so let's carry that through to the next. So look at this slide. This is a girder loaded with the beam end reactions. So we have 3-point loads of 17 kips, and the reactions are 27 kips for that loading. So if we consider the shear force diagram, we have a maximum shear 27 kips at each end. And then if we consider the bending moment diagram, we have a maximum bending moment of 216 kip feet. Now let's look at the alternative. The alternative is to consider a girder subjected to a uniformly distributed load. So in this case, we could figure out that the tributary width for the girder is going to be equal to 30 feet. There's 15 feet halfway to the next girder on the left, 15 feet to the halfway to the next girder on the right. So then we could say that the uniform loading W is going to be equal to Q times T sub W. So that's going to be equal to 100 pounds per square foot multiplied by 30 feet, or that's going to be 3,000 pounds per linear foot, or 3 kips per linear foot. Okay, so now we know where this loading up here comes from, and that gives us reactions of 36 kips. So we can sketch the shear force diagram. It looks like that, 36 kips on either end, and we can sketch the bending moment diagram, and you can see that in the middle of the beam we end up with the same bending moment, 216 kip feet, that we had in the other case. So when we compare the different values, what do we see? We see that the shear force is higher for the uniformly loaded beam than it is for the beam loaded with point loads, but the bending moment is the same, right? 216 kip feet in both cases. So it works out actually that if we were to superimpose the bending moment diagram from the uniformly loaded beam over top of the other bending moment diagram, that the bending moment diagram due to the point loads is actually inscribed on the bending moment diagram due to the uniform load. Okay, interesting. Let's look at another case. Note that the filler beams have changed in this case. Instead of having 3 interior filler beams in each bay, we only have 2. So that means that the spacing of the filler beams is now 8 feet instead of 6 feet. So we're going to look at the same girder again. We're going to look at one of the filler beams in that same bay, bay AB, and we're going to do an analysis. So if we consider the filler beam in this case, then we say that the tributary width is now equal to 8 feet instead of 6 feet. Q is still equal to 100 pounds per square foot, so we can calculate the uniformly distributed load. W is equal to Q times T sub W, so that's equal to 100 pounds per square foot multiplied by our tributary width is now 8 feet, so that gives us 800 pounds per linear foot. So we have a distributed load up here. W is equal to 800 pounds per linear foot. All right, now if we look at how the filler beams frame into the girder again, that means that we have a reaction force there and a reaction force there. So that reaction force, R sub B, is going to be 1/2 of 800 pounds per linear foot multiplied by the length of 30 feet. So let's see, 800 multiplied by 30 divided by 2 gives me a total of 12 kips. So the reaction at each end of the filler beam is 12 kips. So that means we have 12 kips coming in from the left and 12 kips coming in from the right. So we end up with a total applied load at every intersection of 24 kips. So if we look at how that's applied to a girder, then we would have a girder loading like this. So instead of 4 spaces at 6 feet, we have 3 spaces at 8 feet. So the reactions are going to be 24 kips. Those are the reactions for the girder. And if we sketch the shear force diagram, we end up with a shear force of 24 kips at the end, and we end up with a maximum bending moment of 192 kip feet. Let's consider again girder with the uniformly distributed loading is still going to be 3 kips per linear foot. That hasn't changed. So we end up with a maximum shear of 36 kips compared to 24 kips now. But the bending moment diagram is gone up. It's now 216 kips relative to a maximum here of 192 kips. What's interesting, though, is if you, again, superimpose the bending moment diagram from the uniformly distributed loading over top of the bending moment diagram due to the point loads, you can see that the bending moment diagram due to the point loads is again inscribed within the bending moment diagram for the uniform loading. So the bottom line here is that when we consider the two options, it's much easier to calculate the bending moment due to a uniform loading. So here we could just calculate the bending moment is equal to WL squared divided by 8. We don't have to worry about shear force diagrams or anything else. So in summary, when we analyze a girder, it's faster and easier to consider a uniformly distributed loading. We get results for the reactions and the shear forces that are a bit conservative, and we get results for the maximum moment that is equal to or slightly higher than the moment that we would get by modeling the girder using a series of point loads. It works out that the maximum moment is the same when there is a filler beam that frames in at midspan for the girder, and the maximum moment is slightly higher when there is not a filler beam that frames in at midspan of the girder. Okay, so it turns out that in most cases, bending moment governs. Shear force doesn't govern as often as bending moment, so we can accommodate the conservatism in the shear force for sake of expediency when we perform our calculations. Another consideration when we consider tributary area is the way that the slab acts or the way that the slab behaves. Many slabs are modeled as one-way slabs, meaning that the slab acts to carry load in only one direction, usually towards the next level of framing, which is a floor joist or a floor beam. Excuse me, the moments that are carried in the slab, if you model those moments vectors as two-headed vectors, those are parallel to the secondary framing, parallel to the floor beams or the floor joists. So in a figure like this, that would mean that a given load that acts here, for instance, would be carried laterally like that and then transferred into the floor beam like that. And that would mean that a bending moment would exist. Let me draw it as a different color. A bending moment would exist in the slab like that, but it also assumes that there isn't any bending in the opposite direction. So the slab would tend to sag like this, sag like that, but there wouldn't be any bending in the opposite direction. So that would be characteristic of one-way slab action. An alternative way of modeling a slab, though, is to consider the idea that it could carry bending moment in two directions. Right? It could carry bending moments both parallel to and perpendicular to the direction of the supporting joists. So when we consider that, though, things get a little bit more complicated. Let's go back to our roof framing plan. We're back to the case where we have a 6-foot spacing on our filler beams. And if we consider the case where load can move in both directions, then the girders would carry a portion of the loading directly from the floor slab, and then the floor beams would be assumed to carry the remaining part of it. So you would end up with a tributary area for the floor beams that would be trapezoidal, and you would end up with these little triangles or diamond-shaped tributary areas for the girder. Now, that alone is fairly complicated, but when we look at the free body diagrams of the floor beams and the girders, it gets even worse. So shown here on the left is a free body diagram for the filler beams. And you can see that there's a uniformly distributed load over most of the beam, but at the ends, the load tapers away to zero where the girders pick it up because of the two-way action of the slab. If we look here on the right at the free body diagram of the girder, then the girder loading is even more complicated yet. So you end up with triangular shaped loading for the distributed load that the girder carries directly from the slab, and then you have the reactions from the floor beams coming into play as well. So generally speaking, when we consider modeling slabs as one-way versus two-way slabs, with respect to tributary area anyways, it's generally considered to be overly complicated to consider two-way action in the slabs, and almost every slab is modeled as a one-way slab when it comes to tributary area. Okay, a final thought is the idea that when we consider tributary areas, we often consider them with respect to gravity loads, and thus the tributary areas are usually horizontal or flat. However, we can have tributary areas that are vertical or even inclined depending on the type of loads that we're modeling. Consider this building again, and instead of looking at gravity loads like dead or live or snow, rain, let's look at a wind load. And if we were looking at a wind load blowing against the long edge of this building, we might consider a tributary area like that. That tributary area would be the area of the facade or the outer skin of the building that would be tributary to the first floor level. And we might use the pressure loading on there, Q, to calculate a line load that would be going into the first level of framing. Alternatively, we might look at the amount of force that's being introduced to the roof level of this building, where we look at the tributary area that's from the roof halfway down to the first floor level. We would take the tributary width or height in this case of that tributary area multiplied by our pressure loading, and then we would get a line loading in terms of W that would be pounds per linear foot or kips per linear foot. Occasionally, when we look at tributary area on facades or wall units, we look at the amount of force that's entering each node in the building. So rather than looking at a strip that has covers the full width of the building, we might look at a tributary area that is rectangular shaped, and then use that to calculate a point load that is introduced at the intersection of one of the spandrel beams with the columns. Okay, that does it for this lecture. Hopefully by now you have an understanding of how tributary areas are calculated and how they're used to compute loads that are acting on members that support slabs and other area elements. We illustrated the idea of an influence area, but we stopped short of showing how to apply that. When we get into the discussion of live loads, we'll show you where that comes into play. All right, see you next time.